Hey y'all, welcome back to another video. Today's first question is, the product of two positive integers is 504 and each of the numbers is divisible by 6. However, neither of the two numbers is 6. What is the larger of the two integers? So first you basically need to prime factorize 504 and then you can take the primes that result out of it and then start splitting them up to make numbers and then pairing them and then making the two integers basically. So you know that it's definitely divisible by 6. So you go up 8, move down to 2, and then move down to 4. So now you have 24 divided by 6 is 4, so now you have 84. 84 you can divide by 12, 12 and 7, and then 12 you can write as 2 to the power of 2 times 3. So now that we have these numbers, we can pair them up. And we know that they have to all be divisible by 6. But neither of them are 6. So basically, the way you can do this is, you can pair up 6's from the 2's and the 3's, and then multiply them with the numbers that weren't divisible by 6 in the first place. So basically what I'm talking about is, if you write this number out as prime factorization, it would look like this. So then you can split 2 to the power of 3 and 3 to the power of 2 into two 6's, because it's 2 times 3 and 2 times 3. So then that would be 6 times 6. And then the spare 2, because there's 3 2's and 2 3's, and then times the 7. So now you can pair the 6's with each of these numbers, in which you would then get 12 times 42. So what is the larger of the two integers? It is 42. I'm going to box that up. Moving on to problem number 2. In the equation 858 equals a times b, the number a and b are both positive two-digit integers. What is the greatest possible value of a plus b? So this kind of has the same idea as problem number 1. You have to prime factorize it. So you can definitely go a 2 at first, in which you would then get a 4, because you divide 8 by 2, so you get 4. Nothing left, go 5, you have a 2. And then you have 1 left, so you move that down, so now you have 9. Now you can divide this by, if you add this up, then that's, that's 6, and then 9. So you can divide that by 3. So you would get a 1, move down to 1, you would get a 4. You would get nothing, and then move down to 9, so you would get 3. You can split this into 11. And since 11 times 11 is 121, then you would split that into 11 and 13. So now we just got to pair these numbers up because we have 4 of them. So there are 2 obvious combinations, and then 2 more not so obvious combinations, and then a million more. But only one of those actually work to get the greatest possible value of a plus b. So the obvious combinations here are 3 and 11 and the 13 and 2, or vice versa with 3, 13 and then 2, 11. But those aren't actually the greatest numbers. So instead, since you know that 11 and 13 are already two-digit integers, you can pull out either 11 or 13. I'm going to pull out 11. And then you would add it to one of the two-digit integers. So in my case, it's 13 now. And I'll do 11 too and explain why it's not the answer. But, first let's go with this one. So then you would get 11 plus, if you multiply 13 by 6, you would get 8, move up to 1, and then 6 times 1, so you would get 78, in which you would then get 89. And you can also do this vice versa with 13, but it's actually not the correct answer. The correct answer here is actually 89. And let me explain why. Because you see that the gap, the space gap between 13 and 11 is 2, right? And if you multiply 11 by 6, then the space gap between 13 times 6 and 11 times 6 gets multiplied by 6. So then you would get 2 times 6, which is 12, as the space gap. So basically what I'm talking about is if we went 13 plus 11 times 3 times 2, and here you would get basically this number, but minus 12. So it would basically be 78 minus 12, but don't write it like that. You would basically 78 minus 12. And as you can see, 13, if you minus that 12 away from it, then you only have 1 plus, and this one has 11 plus. So that means that it's reduced the fall, but not enough. So in this case, 89 is the correct answer. Moving on to problem number 3. How can we tell from looking at the prime factorization of a positive integer whether or not the integer is a perfect cube? So this question is a little bit more complicated since it is an explanation question, but we'll get through it. So let's say that you've prime factorized like a random number, and its primes, the primes that you get out of it are like p1 times p2 times p3, all the way to like how many p's you want. And pretend they have exponents e1, e2, e3, etc., etc. So the way you can tell if this prime factorization is perfect cube is by if you can pull out a 3 from all of its primes that it's gotten out, and you can put it, and it still is a whole number left, so like e1 divided by 3, and then times p2, e2 divided by 3, and then p3, e3 divided by 3. And then like blah, 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 blah. If all of them can keep going like this, and you would still get a full number, then this is a perfect cube. This number is a perfect cube because you've been able to pull out a 3. There's the same concept with a perfect square. However, the perfect square concept is that if you pull out a 2, then it still works. Then it's a perfect square. If you can pull out both a 2 and a 3, then it's both a perfect cube and a perfect square. So let me demonstrate with, let's say, 64. 64, is 2 to the power of 6, and those are its primes. So then 2 to the power of 6, you can write it into 2 to the power of 2 times 3 if you pull out a 3. So this number, 64, is a perfect cube because you've been able to pull out a 3. It's the same concept using 64 again with the perfect square, as I said. If you pull out the 2 here, 2 to the power of 6 would also equal 2 to the power of 3 to the power of 2. So this is how you prove that it's a perfect square. This is how you prove it's a perfect cube. It depends on the exponent at the top. So yeah, that's the end of this video. I hope you guys learned something new, and I see you guys in the next one. Bye!